Hello everyone, and thanks for attending this talk in CppNorth. I'll be talking about unveiling type erasure in C++ today. It's right at 2:30 in the afternoon. Everyone's had great lunch, some great desserts afterwards. So I think it's a great time to steal an afternoon nap. And in the interest of that public service, I thought I'd talk about type erasure today. So before I get started, I'm a new face for probably most of you. A bit about me. I'm a C++ software engineer based in Chicago, working for a high-frequency trading firm. As you can guess, my interests lie in finance and low-level programming. And I'm quite excited. I'm grateful for this opportunity that CppNorth provided to talk about type erasure today here. Quick overview about the talk. I'll start off with an example of type erasure in the standard library, specifically talking about std function and why we need a std function-like class in the standard library. Then I'll talk about building our own type erased component, again, delving deep into std function and how std function is implemented by most of the implementations. Then I'll talk about the cost of this type erased class, particularly focusing on the performance costs. And then I'll delve into std any, and we'll have a look at a different implementation of type erasure. So let's get started. Imagine you're building your own library, and you want to provide the clients of this library with a filter range method. This is quite a simple method. It takes in a vector of integers as an input, a function to filter this input vector on, and returns an output vector, which is the filter vector. So all it does is iterates over this input vector, applies the filter on function. If it returns true, it pushes the element into the resulting vector and returns that output. Since you're writing a library, the goal of this function is to be as generic as possible. So as long as the client provides you a callable, which takes in an integer, returns a boolean, the client should be able to use your filter range function. So it should be usable by, say, a free function, a lambda, or a functor. The interesting thing to note here is that the filter range function is not templated. Like ideally, you don't want it to be templated. You want to have a concrete type of the function as like the second parameter. You want that to be a concrete type, and yet it should be assignable using three completely different types. So a free function, a lambda, or a functor. These are three completely different concrete types in C++. And the client should be able to pass these. So how can we do this? Well, the first thing you might say is that, I just said that it doesn't have to be templated, but why not? Is there a strong reason for that? You might say that this concepts have been here for a while, since C++20. So why don't we just use a std invocable concept here, have the function signature in there, and the filter on function could be a templated function or like use auto in this case. And I completely agree with you. I think this is a great solution for this problem. There's no reason that like a filter range function like this cannot be templated. Using a std invocable concept is a great solution for this. But there are some cases where you either don't want it to be templated or it cannot be templated. For example, borrowing a use case from like my industry, imagine that there's a market data subscriber class. Now, what this class does is that it subscribes to market data from various different exchanges, and whenever a new instrument comes in, it filters the instrument based on a filter function that the client has provided, and if that filter function returns true, it stores that instrument or like passes it on to a different component to process that instrument and send orders for that instrument. So the idea behind this class is that the client should be able to pass a filter function on construction, and it should be able to copy the function and store it inside the class because it's not immediately invoking it. It's invoking it at a later point where a new instrument is received. So although you can argue that the constructor can have a std invocable concept, like in this case I have it on line 3, the templated type T is constrained by a std invocable concept, that works fine. but how do I store it in my class? So I need a concrete type here for this function. Just for the simplicity, for the sake of simplicity in this presentation, I've taken the example of this filter range function, but concepts don't work for us in this case. The next thing you might say is, well, why not use good old C-like function pointers? We want the client to be able to pass us a function, can simply use a function pointer, and can invoke that function. Function pointers have some clear downsides. The first and major downside is that all the callables that are referred by a function pointer need to be stateless. So, for example, a lambda that captures some state or a functor that has some state cannot be referred by a function pointer. The second downside, more from a design perspective, is that there's pointers, lack of value semantics. Ideally, you want a solution which is prettier and safer to use. And the third downside, which is a bit of a nitpick here, but it's still quite important in terms of safety in C++, is that you need to perform null checks whenever you are using a function pointer. Obviously, there can be a wrapper around it which does it for you, but I think this is an important point. So, taking a step back here, concepts don't work for us, function pointers don't work for us. Essentially, what do we want to achieve? We have three different concrete types, or a couple of different concrete types that share a common interface, and we want to be able to represent them with a single concrete type. One of the first things when I learned C++ was object-oriented programming, and quickly when learning object-oriented programming, interfaces and runtime polymorphism comes up. And essentially, with interfaces, what we achieve is that there are different implementations of an interface, like different derived classes, which share a common interface, which can be referred to by using a pointer to the base class. And it sounds like this is something similar to what we want to achieve. Like, there's different implementations which share a common interface, and we should be able to refer to them by a concrete type, which could be a pointer to the base class. So let's try using interfaces here. Here I have a base class iFunction, which has a pure virtual method, which is the function operator overload method, takes in an integer, returns Boolean. And then I have two derived classes. They inherit from this interface iFunction, and they have their own different implementations. isEven functor has an implementation that checks whether the input integer is even. isOdd functor checks whether it's odd. Now my filter range function could look something like this. I can simply pass a pointer to the base class, and the client, all the client needs to do now is create objects of this isOdd functor or isEven functor, their own implementation, and they should be able to use this filter range function. Well, this looks great. So the idea was that we want to be able to represent different function types using a common callable interface. This is a concrete type, no templates. There's still pointers, but it looks like it looks great. I mean, this is exactly what we wanted. Well, although this is pretty good, it's still a bit further away from what we are looking for. There are some downsides of this inheritance-based solution. The first and the biggest downside of the solution is that all callables need to inherit the interface now. So if you pass any callable to it, it needs to inherit this interface iFunction. So imagine there's a third-party library which implements this complicated function which takes in an integer, returns a Boolean, for the sake of it, let's say an isPrime function. There's no easy way that we can use this isPrime function directly without having this inheritance hierarchy. So all callables need to inherit the interface. It's quite restricted. It's not possible to pass third-party functions. There's still pointers, lifetime management, lack of value semantics. So it's still a bit clunky. And this is where std function shines. By simply using a std function with the correct function type signature, takes in an integer, returns a Boolean, I can now pass a free function, a lambda, or a functor to it. Okay, the interesting thing to note here is that These are three completely different types in C++, which are assignable to this common concrete type, a std function with a function signature with a parameter int and a return type boolean. And this is exactly what type erasure achieves. As we'll see, std function implements type erasure, and this is exactly where type erasure is quite useful. So the big question is, how can we implement a class like std function, which can have these unrelated types, free function, lambda functor, be assignable to a common type? And it's not, although I'll focus on std function and standard library containers, you can extend this to any object-oriented like programming hierarchy that you might have seen before. For example, the classical example is that there is a class animal, which is an interface. Say it has a pure virtual method called make noise, and then there's some derivations of that class. Say cat, it makes some noise meow. Dog, it makes some noise barking. So the classical example or the classical implementation of this is using a base class and a derived class hierarchy. But other languages, like Python, have something called duck typing, which is if it walks like a duck or quacks like a duck, it should be a duck. And type erasure is quite useful for something like that. So with type erasure, now these derivations, now these concrete objects of, say, a dog or a cat, don't need to derive from the common base class. As long as they implement a common interface, they should be able to be used by, they should be able to assignable to a common concrete type. And this is exactly what we'll see with a std function implementation. So different concrete types having a common interface are assignable to a common concrete type. Let's have a look on how we can implement a std function-like container. So the requirements of this class is that it should be constructible from unrelated types, and it should have a common callable interface. If we take a step back and notice, the second requirement was already satisfied by the interface solution. So although it wasn't constructible from unrelated types, all the types that we used in this interface solution had to be bound by an interface hierarchy. So it wasn't really constructible by unrelated types. The second requirement was already met. All these types had to have a common callable interface, and the interface I function ensured that that this requirement is met. There were some downsides of the interface solution, as we saw. The first downside was that everything needs to have this interface hierarchy. Every class being used needs to derive from this I function interface. The second downside was that as a result of this, we cannot use third-party functions. Like if there's a function in a third-party library, we simply cannot inherit and use that. And the third downside was that there's pointers, lifetime management, lack of value semantics. So let's get back to interfaces and try to address those downsides. Although I said that we can't use third-party function, I lied. Basically, what we can do is if there's, say, an interface function concept that enforces this, that has this pure virtual method, takes an integer, returns boolean, the function call operator overload. What we can do is that if there's a third-party function is prime, or let's say in this case there's a is even functor that inherits from this function concept. This is all good. We can use is even function, but now if there's a third-party function called is prime, say this is in a third-party library's namespace, all we really need to do is make a functor out of this. So here I have a new class called is prime function. All this does is derived from the function concept interface. So the library, one of the libraries is providing this function concept interface. The library that has the filter range function, let's say the CppNorth namespace. And then what I want to do is that in my application, I want to use the third-party is prime function. all I really need to do is define my own class, derived from that interface function concept, and implement the virtual function override. So it is possible to use third-party functions. It's just a bit cumbersome. Let's try to abstract this away from the client. Instead of me making this class each time in my application, inheriting from the function concept, simply to call a third-party function, let's try to abstract this from the client. The thing to notice is that there are some common things between the is-even functor that we previously saw and this is-prime function. Although the is-even functor, for example, was provided by the library that implemented filter range, and is-prime function is a function that I created in my own app. There are some common things between these two. The first common thing is that both of these inherit from the same concept. To get the technical keywords right, both of these inherit from the same interface. The second common thing is that they both, as a result of inheriting from the same interface, they both have to implement or override the pure virtual function. So now the goal becomes to create a generic class derived from function concept, constructible from any callable. Instead of the application having to create this class, what if I provide a class that is constructible from any callable as long as it takes an integer, returns Boolean, and the client can now simply use this class's object. Whenever I hear the keyword generic, the first thing that comes into my mind is templates. So let's just take a template. Here I have a function model class. All it does, the only thing I've changed so far from say is-even functor or the other implementation is having a templated type. So this function model is a templated type. It inherits from the function concept class. As a result of this type being templated, the constructor simply accepts any object. The parameter of the constructor takes in the template type, func type, so you can pass any object of type func type. All it does is moves that object and stores it in the class. Because this inherits, this is derived from function concept, it needs to have an override for the function call operator. So this class now makes, although you can pass, as per the template type, you can pass any type to this class, but it does make two implicit assumptions about the type func type. The first implicit assumption that's made in the constructor is that it should be movable. I'm using stored move there, so the type should be movable. And the second implicit assumption is that as a result of the function call operator overload, I'm storing the type and invoking it with an integer. So it should be invocable by an integer and should return a Boolean or something like a Boolean. So something that is convertible to a Boolean. We can later make it nicer to ensure that there's better errors and these constraints are enforced at compile time. But this looks great. Now we've got a function class, a function model class. It is constructible from any type, makes some implicit assumptions, but these are assumptions that we expect. This type should be movable, but the important thing is that it should be invocable by an integer and return a Boolean. So now the client, instead of having their own definition of a class, what they simply have to do is create create a function model class, pass in their function here, and no matter what, if it's a third-party function, if it's a lambda, if it's a functor, that's fine. They can pass anything here. They just need to give me a pointer to the function concept, like a pointer to the base class. My filter range function now accepts a pointer to the base class, and all the client needs to do is create an object, a function model, and pass it to me. One thing that I've added here is instead of directly constructing the function model object with the is prime free function, I've explicitly defined the type, and that is because the is prime function is a free function in this case, and decaying that would point to the function pointer. So this is just what I described. We've now got a function concept class, a function model, which is a templated derived class, which inherits from the function concept. As a result, it implements the function call operator override. Another thing to note here is that previously this library, which had the filter range function, was giving me some of the filtering methods. For example, it was providing me with an is odd functor or an is even functor, and these were derived from the function concept. But even these types no longer have to be bound by an inheritance hierarchy. So is even functor can now be any free, like a free type, not bound by an inheritance hierarchy. And the client should be able to use this as long as the client wraps it in a function model. So line 33, 34 here, for example, all the client is doing is wrapping that is even functor into a function model. So basically, now the client can use any callable as long as it takes an integer and returns something that looks like a Boolean, that is convertible to a Boolean. All the client needs to do is wrap it in a function model. And this is exactly what type erasure achieves. With type erasure, it hides the concrete type of an object with a uniform interface. The uniform interface in this example being the function called operator overload. Like it should be invocable by an integer and return a Boolean. So it hides the concrete type of an object with a uniform interface, and it does not require these objects to be bound by an inheritance hierarchy or be related to each other. These types could now be completely unrelated types. To recap, the filter range can be called using any callable wrapped in function model. The client has to wrap the function. There are some downsides though. The client has to wrap the function in a function model object. It's a bit clunky. The client is still responsible for lifetime management. I've used raw pointers so far. I know that some people will be disappointed with that, but I promise I'll change that in the future slides. And there's a lack of value semantics. It will get better. There's not gonna be any raw pointers soon. So let's do the dirty work for the client. Let's abstract all of this away. And although we've got very close, the client can now pass any callable as long as it's wrapped in a function model. The ideal solution is that the client simply passes me that callable. Like the client doesn't need to wrap it in a function model or something like that. So now I have, so far what I've simply done is define a new class called function, have some inner classes, the function model and the function concept that we previously saw. So far no changes really. Now, what we want to do in this function class is that the client passes me any type as long as this type is invocable and returns a Boolean. I should just I should just wrap that type into a function model and store that as a pointer to the function concept class. So essentially this function class, one, should not be templated because we want a single concrete type. We don't want different instantiations of a templated type. But even though the class should not be templated itself, it should be constructible by any type as long as it's a callable, which we can enforce with C++20 concepts. So although this class is not going to be templated now, the constructor is going to be templated. This constructor now this class is now constructible using any type, and all it does is wraps that type into a function model type and then stores that as a pointer to the concept. This is exactly what the client was doing. In order to use an invocable, the client was wrapping their function into a function model, and my filter range function was expecting a pointer to the concept. All I've done is just abstract that away into a new class called function. But this looks much better now. This function class obviously needs to provide a callable interface to the client. So all it does is takes an integer. One thing that I've introduced here is that if the function if the mfunc pointer is null, it throws an exception. This is similar to the behavior that stud function has. But this looks much better now. The client can simply, my filter range function simply needs to have a parameter of type function now instead of any pointer to function concept. All the filter range function needs now is to accept, is to have a parameter of type function. And the client can now pass any invocable. And as long as it can be wrapped into a function model, that is, like, there's some implicit assumptions about that it should be invocable using an integer and return a Boolean-like value. As long as those are met, it's all golden. The client should be able to use this. And this implementation is very similar to a stud move only function. I've used, the reason why it's move only and not similar to a stud function is that I've used a unique pointer there. I think it's not scrollable on there, but let me see. Yeah. So on line 34, I've used a unique pointer, which makes this class only movable, not copyable. But this looks much better. The client can now simply use this class to pass any function, not bound by any inheritance hierarchy. The interesting thing to note here again is that although the type of this function being passed, say a free function lambda, a functor, the type information is not being lost, it's just hidden. So the function model concept does have the concrete type information as part of the template. Although the class function sort of loses the type information because it stores a pointer to the function concept, the function model still has the concrete type information. And at a later point, we'll see why that's important. First, let's try to make this copyable. Get a bit closer to stud function, which is copyable. Making this copyable is pretty simple. All we need to do is have a clone function in the function concept. This clone function, again, is a pure virtual function. The function model overrides this function, provides an implementation, and all this does is that it copy constructs the function model itself. So it creates a unique pointer of function model, and all this is doing is calling the copy constructor, and it returns a unique pointer to the function concept. My function now, the copy constructor of my function now, simply needs to call this clone function of the function model, and that's it. The filter range function, like now that it's a copyable, now that my function is copyable, it provides value semantics. The filter range function can simply have an object of type function and call this filter range by any type. This is the common prototype design pattern where we have a clone method, which is a pure virtual function, and then the function model overrides that in the implementation. To recap, now we have the filter range function that can be called using any callable. There's no pointers or lifetime management. It's all abstracted away from the client. We've got a copyable function class, this value semantics, but there's still one downside, which I've been talking about. There's implicit assumptions in this type being passed about the callable, that it should be one, movable, and two, invocable by an integer and return a Boolean-like object. And so far, it only works with this single concrete signature, which takes an integer, returns a Boolean. So since this is a talk on sort of type erasure and particularly about how to implement a stud function-like class, let's make it more generic. it's just to play with some more templates. Here I have a function class which is templated. Previously, this was a non-templated class because we were only implementing a common signature which takes an integer, returns Boolean. But now I have this templated function class. It's not defined. I've only defined a specialization which expects a return type R and a couple of arguments, variadic set of arguments called args. This is just some play with concepts. We can enforce at compile time the type of this function. So it should be invocable by the set of arguments. I think there's after the stood invocable, there's an error with how the bracket should be, but that's fine. Essentially, it should be invocable by a set of arguments, the args variadic template, and the next thing we want to enforce is that once it is invoked by these arguments, the return type should be the same as R. I'm not sure if stood function has stood same as R or stood convertible to R, but it's just a detail. The next thing is that the interface for the operator overload that this function now provides is a bit more generic. It's invocable by this set of arguments and returns the type R. And this is a functional implementation of stood function. It just works. It's clonable, it's copyable, so it provides value semantics. It can be constructed by any type as long as it's invocable by the set of arguments that you provide and returns the type R. Let's talk about the performance cost of this implementation. There's primarily two costs. One, it does heap allocation on construction. So whenever a client provides a type, a callable to this, it wraps it into a function model and does some heap allocation. The standard, the implementations do optimization for this, which is called small buffer optimization. We'll shortly see how that's implemented. The next cost is that there's virtual function calls. And I think it's a pretty small cost. Most of the times, I can get by with heap allocation on construction. I think that's important to optimize. For most of the systems, the virtual function calls are fine. But there's an optimization for this called manual virtual dispatch, which we'll later see when we come to std. Let's talk about small buffer optimization. So the idea behind small buffer optimization is similar to small string optimization, which is if the function being passed, or if the type being passed to this function is small enough, instead of allocating memory on the heap, let's just have a pre-allocated memory on the stack and construct this type in place in the stack. So here I have, just for an example, a storage model type, which is the threshold type, which defines the threshold size of my stack allocation. So if this function gets a type which is of the storage size or smaller than that, it's gonna construct the function in place on the stack in the byte storage M storage. And if the size of the type being passed is bigger than that, it's gonna do heap allocation. Another important thing to note is that alignment is important here. So I've done align as, you can see in my byte store, I've aligned it as the storage model type. Alignment is important for casting and construction of the type in this byte storage. So now my constructor looks a bit different. My constructor first does a const expert check of the size of the type. If the size of the type is smaller than my storage size, it does in place construction at the buffer in the stack. This is I've used stood construct at, which internally uses placement new. So it does placement new construction at this size at the address of the storage. And if the size is greater than my threshold size, storage size, it does a heap allocation. So just fairly straightforward, just doing some tricks around pre-allocated storage on the stack and placement new. This is quite common in pre-allocated memory pools, for example. The clone function now needs to do something a bit different. Previously, the clone function did not have any parameter, but now if the function that it's cloning was constructed on the stack, it needs to copy the function onto the stack of this onto the storage address of the target function. So now the function needs to pass the address of the storage when it's cloning, and if the size was smaller than the threshold size, it's gonna construct a new element at the address of the storage. Otherwise, return similar to before. Otherwise, it calls the copy constructor and returns a newly allocated object on the heap. Yeah, so that's all about small buffer optimization. Before I jump into std.any, bit of a detour, and I want to talk about type safety in type erasure, and particularly just touch a bit upon shared pointer. So imagine we have this class noisy foo. All it does is that it makes it outputs something on construction and outputs the destructed noisy foo message on destruction. Although you would never see raw pointers, especially a void pointer in modern C++, just for the sake of this example, imagine you have a function back in the C days used to take, like generic functions used to take void pointers, and this function, say, has to do something using this pointer and then free up the resource to delete this pointer. Is this valid code? Not really. It wouldn't compile because as per the standard, this is not valid code. An object cannot be deleted using a pointer of type void star because void is not an object type. So back in the C days, how this would be implemented is that along with a void pointer, there would be a deleter function being passed, and this deleter function, because at the time of the creation of this pointer, you are aware of the concrete type. It's safe to typecast into this concrete type and call the delete. So instead of just calling delete on the raw pointer of type void star, you would have a function that does it for you. What about unique pointers? Can we have a unique pointer of type void, which, although it's a pointer of type void star, the object being stored is noisy foo? Well, this should logically be possible because at the time of the creation of this unique pointer, we have the concrete type of the object. We know it's noisy foo. And similar to before, it should simply call the destructor, like typecast it into noisy foo and call the destructor. But this is not possible. GCC 14, I think, gives a nice error. Static assertion failed, can't delete pointer to incomplete type. Clang 19, bit of a cryptic error, invalid application of size off to an incomplete type of void. But basically, it won't compile. Why is this? If you see the template arguments of a unique pointer, it actually takes two types. I've never used the deleter, but it takes two types. The type of the the template type that it's storing, type of the pointer that it's storing, and the second type is the deleter type, which is defaulted to std default delete of this pointer type. So when I'm creating a unique pointer of type void, it's actually the deleter is being defaulted to std default delete of type void, which is invalid. Can't delete a void pointer. So how we would do this with a unique pointer is again having a deleter similar to what we saw with a raw void pointer and passing that deleter to it. Sure, okay, this works fine now with a custom deleter, but now I have a void pointer pointing to an object of type noisy foo. Say I have another type called noisy bar, which is a different type, but has a common interface. I should be logically able to assign this different pointer, which has a common interface to this void pointer. Like ultimately, they are both void pointers. I should be able to assign one void pointer to the other void pointer, ensuring type safety. But this is not possible. This will throw an error. And the reason this is not possible is actually is straightforward to see, because the previous type that I created has a deleter of type foo deleter, which is a different concrete type. And now I'm trying to assign, like the type of my pointer has the pointer type as void, sure, but the deleter type as the decal type of foo deleter. But now I'm trying to assign it to a whole different template instantiation of stored unique pointer, which has a different concrete type of the deleter. So that's not possible in C++, of course. What about a shared pointer? All I've done in this example is change the unique pointer to a shared pointer. Again, I think when I used, while creating a unique pointer, when I used new noisy foo, it might have raised some eyebrows. So I made sure I fixed that and used stored make shared. What about this? If a unique pointer does not compile, I'd expect this to not compile as well. But to my surprise, this works. And if I assign this to a pointer of a different type, different object type, say noisy bar, that works as well. And the interesting thing to note is that although these are void pointers, they're constructed and destructed in the right order. So having a void pointer to an object type should ideally just lose the information of that type. And like not ideally, but it would just lose the information of that type. And when it's destructed, it wouldn't know which type to destruct. But somehow shared pointers store the information of the object type in a void pointer and are able to construct and destruct it correctly. The difference is that in the unique pointer, although the unique pointer expects two templated arguments, the class, the type T and the type of the deleter, but shared pointer only has a single type argument, the type of the pointer. But somehow it's still able to store the type of the object being passed to it. And this is because shared pointer does type erasure internally. So shared pointer, unique pointer only stores the template type information. Shared pointer stores both the template type information and the object type information. And shared pointer uses type erasure to call the correct destructor. So I'll quickly go over that, wouldn't get into much details. But the overview is that in a shared pointer, it stores the pointer to the type T, which is like the pointer to the object, and a pointer to the control block. The control block has various things, a reference count, which when a shared pointer is copied, it just increases the reference count, and weak count and some other data. The particular data that we're interested in, is the custom deleter. With every type erased type erased class, shared pointer also has a templated constructor. That's common in every type erased implementation. The interesting thing to notice is that unlike unique pointer, a shared pointer has the pointer of the type in the templated templated class shared pointer the type T, which is the type to the pointer. But the constructor is templated as well on a different type, so the type Y in this case, and all it expects is that the pointer to this type Y is convertible to the pointer to type T. And although the default deleter is stood default delete of this object type, you can pass on your own deleter. And that's the critical part here. The default deleter is not the stood default delete of the type of the pointer type T, which would have been void in our case, but instead it is the deleter for the actual object type that you pass to a shared pointer. But again, the challenge comes in: how do you store? You've got a templated constructor. How do you store the type of this deleter? And the shade pointer does exactly what I previously described. It has a control block base, which is a concept, and then it has a model. This concept model hierarchy is very common in type-based implementations. What it does is that it stores a pointer to the control block base, and on construction, it just passes the object type to the control block and stores a pointer to the control block base. So I won't go into the details of this. You can check it out in the slides. It's exactly the same as the previous implementation. The last thing that I want to talk about is stood any, and as part of this, discuss the second optimization, which is manual virtual dispatch. As per CPP reference, the class any describes a type-safe container for single values of any copy constructible type. The two important things here are that one, it's a type-safe container, and two, it has the type has to be copy constructible. Now I have to admit, I've never seen stood any in the code I've written or I've explored. Never seen stood any being used. I'm sure there are some use cases. If you have some, I'd be keen to know. But there was one use case that I recently came across, which was not exactly stood any, but a classical example of type erasure, where someone wanted to have the key of a hash map to be any type, as long as it has the hash function. Like, as long as it overloads the standard hash function, I should be able to use it as a key in my hash map. So although it's not exactly stood any, it's basically any type which overloads this hash function. And this is a classical example of using type-based classes. But the implementation of stood any is still interesting. With stood any, we can assign it any type. In this case, I'm assigning it an integer. The important thing to note is that although I can assign a double to it, an integer, it still does not, it hides the information of the type. So with this any, it's not templated, so the type information is hidden, but it's not lost. I can extract out the type information from this object. So I can print it, cast it back to the specific type, and if I try to cast it back to a different type, it's gonna throw an exception. So let's have a look at implementing it. Again, the first thing common between all the type-based implementations is having a templated constructor. So stood any should be constructible using any type T. It simply forwards that and stores a pointer to the concept type, similar to what we've seen before. Previously, stood function had a pure virtual function for the function call operator overload, but now what we want to have is to be able to access the type of this function, the type of the object being passed. So we'll have a pure virtual function to access the type. Stood type index is, I believe, was introduced in C++ 17, maybe 11, not sure. But it's just a copy constructible wrapper over stood type info, which is not copy constructible by default. Again, exactly the same thing here. There's a concept model hierarchy. It overrides the type, and now I can access the type from the pointer to the concept. So pretty simple. Classic type erasure. The critical thing to note is that the type, although it's hidden, it's still accessible. It's accessible via this interface hierarchy. So next, I want to discuss the second optimization, which is manual virtual dispatch. So how do we do this without having this virtual function calls? This is sort of going back to the old C way of having raw void pointers. I have a templated constructor here of templated on type T, and the value, I'm simply storing it as a pointer to this. I'm creating a new object of this type T on the heap, and simply storing it into a void pointer. At this point in the constructor, I do have the knowledge of the type, so it's easy to store the type of this. Simply get the type ID and store it in my class. But the challenge becomes on how to delete this in a safe manner. So the destructor should be able to call delete on this heap allocated object. And as we saw previously, I cannot simply call delete on a void pointer. So this is a challenge. How do we implement the constructor? As I said, we do have the information of the type in the constructor. So we can adopt a technique that we previously saw. Simply store a function, which is let's call it a deleter function, m deleter. What this will do is cast the pointer back to the concrete type and call delete on it. The destructor now simply checks if there's any value stored in the pointer, call the deleter callback. And this is it really. So we can have a clone function similar to this, which is defined at the construction, and all the clone function does is casts the pointer back to the type T, the concrete type, and calls a copy constructor. So with this implementation, without the use of virtual functions, we are able to hide the type. So this any classes now can be assigned type of any object as long as it's copyable, and you can access the type of the object in a type-safe manner. So to recap, type erasure enables the use of unrelated types with a uniform interface. These types do not have to be bound by an inheritance hierarchy. As a result of this, it reduces dependencies. So you can have completely unrelated types from third-party libraries, your own application. As long as these have a common uniform interface, you can use type erasure to store them, pass them around. And it's quite prevalent in standard library. As we saw, it's used in stored function, stored shared pointer, stored any, other places as well. And it achieves duck typing, which is a common pattern in other languages. So as long as they have a common interface, you should be able to use them. And I think this is why it's quite an interesting pattern in C++. This was when I could reason about interfaces having pointers to base class to access the implementations, but type erasure was quite interesting when I first learned about it, because it allows assigning completely unrelated types to a common type, which is quite interesting in a strongly typed language like C++. But yeah, that's all I had to say. Thank you so much for patiently listening to my talk. And if you have any questions, I'm happy to answer them.
Hi, thank you for that. You asked for an example of std_any being used in the wild. One place I've seen it used is when you are creating an object and you want to use it like in a general framework, like in a simulation framework, and that object has additional variables that it references, passing in like a vector of std_any to capture like the context of everything around it, like all the references it makes. That's one place I've seen it used. I can't comment on the quality of the implementation, but that,
Yeah, I think it's, I see it as I think it's a common thing that it's a modern void pointer. And I think most of the implementations are rather lazy to use std_any than like something else. So yeah, but interesting to know that you've come across it.
Hi, Sarthak. It was great one. So I learned a couple of new words from C++. May I ask you about, you used unique PTR for storing the type. Could we use their type traits? Because you use some of type traits here, but like did you omit them like intentionally, or it was out of the scope? So like for checking the type of the function, like is the same. So checking the type, you can just check type with type traits. Why didn't you use them here?
You mean sorry, just to confirm the question, you mean
like enable if, for example. So you could enable the template, not store the unique PTR inside, but enable it if the type, like certain type. Could we use this idiom here, for example, enable if or no?
So you mean like in the filter range function, for example, just use constrain the function using a type trait instead of using a stored function or something. I think if I get your question correctly, I think I touched upon a bit. There are cases when we want to be able to store the function in the class, for example. For example, the market data subscriber that I showed. In that case, I want to be able, the client, I should be able for the client to be able to pass a function and invoke it at a later point. So I want to copy that function and store it in my class in order to invoke it at a later point. So although I can constrain the function being passed with a type trait, I want to have a concrete type of the class. I don't want the class to be templated. So I can I can constrain the constructor, but I want to copy the function and store it in my class.
I see. So you don't use the names of the type exactly, but just some directional qualities of it, right? So it's copyable. It has operator like functor.
Yeah. So I think so. This is the example I was talking about. Although I can in the constructor of this class, I don't want the class to be templated. Say due to whatever reason. Just say I want to limit the number of symbols during compile time, but I can constrain the instrument filter function here. But I want to invoke that at a later point. So this class needs to somehow store that function.
Okay. Thanks. Yeah.
All right. Thank you so much.